All right, gang, let's go ahead and get it going. Can I get a sound check in the audience? See if you guys can hear me. Awesome. Looks good. Okay. Are there any questions, comments, concerns, hopes, fears before we get started today? Everyone got project 1 turned in just fine? So I think the record for the fewest number of lines to complete the first project, I believe, is 6 lines. And I don't think it's possible for it to be lower than that. At least I was able to do it 6. 6 real lines, man. I don't mean like, let me rephrase that. 6 instructions. Yeah, man. You guys want to see it? All right, let's do that. Let's bust out of this PowerPoint thing real fast. Let me out. Okay. Well, let's see. Hold on. That's what we're gonna do next time, or at the end of class. All right, so here we go. Here's gonna be the 6 line. Let's save it as a .v. No extension. Project 1 .v. Yeah, I want to replace it. Okay, so here's the thing. Before people start to get really salty, everything I am about to do, we talked about in class. So there's nothing that I'm about to do that we haven't talked about in class. So here we go. Line number 1. So 6 lines. Module, top, and we had what was it? A, B, C, and Y. That's line number 1 in module. That's gonna be line number 2. Well, actually, it's gonna be line number 6 when we're done. So input A, 4 bits for A and B. A 1-bit input for C, 4 bits of output for Y, and then the magic, assign Y equals C, the ternary operator. So the first one is when C is equal to 1, so Y is equal to A minus B when C equals to 1, and when C is equal to 0, then Y is equal to A plus B, semicolon. Done. Ship it. 6 lines. Pour the salt. I mean, it's not really, you can't really brag. You can't really flex when you're the professor and you're with students who are doing this for the first time. Okay, so we talked about it. Maybe we breezed over it. Maybe you weren't fully paying attention. No, we weren't graded on optimization. As long as it passed the test benches, you're all good, right? Okay, so let's unpack what we just did. So up here, this should be pretty normal, right? We had inputs. The only thing that's a little bit different is writing class. Normally I do this. You know, I put all my inputs on one line just because I like to do that, but here I laid them out. As long as they're all the same number of bits, you can put that all on one's line. Hold on, Edward asks, what was up with the 2's complement instruction? That went through me. So I wanted to say, because I needed to say that it could be a negative number. And I knew that I couldn't just say negative. So I just specify that it was 2's complement. Howsoever, Verilog uses 2's complement by default, so you didn't actually have to do any like additional stuff, unless you were doing it with the adding modules and stuff like that. in which case you took advantage of the fact that it was 2's complement to lay it down. Okay, let me unpack this. This is called we talked about it in class. This is called the ternary operator. Let me put some comments here. Ternary operator, right? So basically the way it works is, assign. Put that in comments. So assign y equal to some condition. So you look at some condition first, then you assign it to if true or if false, right? So we're saying we're going to make an assignment to y. We're going to look at c, and if c is true or if c is equal to 1, then you give it that. And if c is false or if c is equal to 0, then you give it that. Liam says he wondered if he could have just used pluses and minuses and let the code do it, but he figured it was intended that we build adders and stuff, man. I never said that. I just said make me a thing that sets y equal to a plus b when c is equal to 0, and when c is equal to 1, give me y is equal to a minus b. All that you got to do the hard way stuff is just an invention of your own mind. I never said you had to do it the hard way. And Joshua says, tried it at first, but it couldn't quite work, so you did it the long way. Hey, sometimes you just got to do it the long way. Like there's no, it doesn't quite work out, and you got to do it the old-fashioned way, right? Which is why I said, like, there's no, like, you're not graded on optimization, right? Like it's just, did you implement logic that worked? Some folks were able to figure out the fast way to do it. Some people did it the long way, and those of you who did it the long way, don't feel bad about it, right? You certainly learned more than the folks that did it this way. So let's see, hold on. Liam and Adrian are both asking about, like, wouldn't an if statement work here? But see, the thing about an if statement is, so this is all combinational logic. If we wanted to go out of our way to make an if statement work, we would have to do this. I would comment out these 2 lines, and I would have to say output reg. In fact, we're going to talk about that at the end of class, so put a pin in that. Output reg y, and then I would have to say always at star begin and end if c begin and end y is equal to a minus b, else begin and end y is equal to a plus b. Right? You'd have to do it that way. That would also work. We'll talk about this business, this less than or equal to business, when we go over the stuff at the end of class. So, any other questions about that? One last thing. So Aiden gave his example, which is totally great. But you said C is equal to 0. You can get away as long as a thing is 1 bit, right? And it evaluates to a 1 or a 0. You don't have to specify, right? It'll get evaluated as a Boolean. So this is just saying if C is the same thing as saying if C is equal to 1. All right, I'll wait for Megan to finish her question, and then we'll do the lecture. You could change it to, if you wanted, if you were just like really passionate about having the addition one be first, then yeah, you could have said if not C. Megan asks, so whenever we want to use an if-else statement, the line always at star must be included. Yes, because this is a sequential logic pattern, which we'll talk about at the end of class today. So if you want to use if-else's and stuff like that, it has to be in sequential logic. It can be, but this just says all of the variables. It says if any of the inputs change, execute. Right? You could have said A or B or C. Right? That would have worked well. Just the same. All right. So, but I'm going to leave that there. Since it is combinational logic, we'll stick to combinational logic patterns right there and say, boom, there it is. All right. So with that, let's go ahead and jump into, minimize that, the lecture for today. We're going to talk about shift registers. And then when we're done, we'll break out of this and we'll go back to do some sequential logic in Verilog. All right, so here's just a list of what we're going to go over. We're going to essentially work through a few examples of shift registers and kind of unpack what the structure is and how they operate. We're going to look at a write shift register, an 8-bit serial in, serial out shift register, a parallel in, parallel out shift register, and we'll look at its operation, its timing diagrams. We'll look at shift registers with inverted feedback and how that relates to what we call a general shift register counter. So let's first look at the write shift register. So when we say write shift, that just means that we're going to take the bits and we're going to pass them to the right. And if you look at this, it sort of should be kind of intuitive that this is what's going to happen. We've got a serial in, we've got a serial out, right? Whatever bit gets put here gets passed through, and then on the next, so on every clock cycle, it jumps to the next flip-flop. And then on the next clock cycle, it jumps to the next flip-flop. And on the next clock cycle, it jumps to the next flip-flop. And then finally on the last clock cycle, it jumps out of the end. So you're taking the bits, whatever bits are in here, 0 or 1 on serial in, and you're just sort of cycling them through the shift registers. Every time the clock pulse happens, and by the way, there's no bubble here. That means this is a rising edge. Set of flip-flops. Every time there's a rising edge, we're going to pass the bit to the right. So if there's a 1 here, then there will be a 1 here. Right? If there's a 1 on 3, there will be a 1 on 2. If there's a 0 on 2, there will be a 0 on 1, and so on and so forth. The only thing that's a little bit sort of, I don't know, well, it's all interesting, but we have the clock enable here attached to this shift thing, which basically just means that if shift equals 0, nothing happens. Right? So if shift equals 0, clock enable is off, so the clock can't update, so the flip-flops can't update, so the shifting doesn't happen. It just kind of sits and nothing does anything. So when shift is 1, then shifting happens. So that's the write shift register. Let's take a look at the timing diagram to kind of illustrate what's going on. So we have our serial input here. This diagram assumes shift equals 1, so everything's going to sort of run. And then here on the first rising edge, right, Q3 takes directly from serial input 1, right? SI is attached to D3 or Q3. Right, so Q3 is going to say, all right, well, what is SI? It's 1. All right, I'm going to go to 1. And then on that same rising edge, Q2, which is attached to Q3, says, all right, well, Q3 is 0, so I'm going to go to 0. Right? Q1 looks at Q2 and says, all right, Q2 was 1, so I'm going to go to 1. All right, and then Q0 says, all right, Q1 was 0, so I'm going to go to 0, right? Minus some delay there. So you can see that 1, and then on the next clock cycle, right, Q2 looks at Q3 and says, oh yeah, that's 1, so I'm going to go to 1. So you can kind of see, though, this diagonal line that goes is the 1 on every clock cycle gets passed down the line, right? And the same thing here where we have 0, right, on every clock cycle. We can see that 0 getting passed down the line, and so on and so forth. Edward asks, would there be a delay between the Q outputs beyond the delay for what the clock is? No, since they're all updating on the rising edge, they all have their own delay. And I mean, you can see there's some delay here, right? So there is some update delay that follows. So they don't update until a little bit of time after the rising edges. But all the delays are independent of each other. They're not like, there's no like sequential delay. It's not like Q0 has to wait for all the delay from Q3, right? Since they're triggered on the rising edges of the clock and they're all getting the clock, they all just only have their own delay. Of course, there's some delay in that it takes, 4 clock cycles for this one to make it all the way down to the last one, right? So you can think of the bits, the shifting of the bits having a delay that's related to the clock cycles, but the actual flip-flops themselves have no delay. All right, any questions, any other questions about the right shift register? All right, in that case, let's take a look at this guy, an 8-bit serial in, serial out shift register. We can draw it on our logic schematics using just this really simple block diagram where we got serial in, we got a clock. Again, notice no bubble, so that's rising edge. And then we've got some serial out. So let's take a look on the inside. Now here you'll notice they used SR flip-flops. Right, and that works just as well. The only thing is, remember, serial in input has to be inverted now before it goes to R to make sure that S and R are always complementary of each other, and you always get the opposites, right? Although S0 is attached at the Q output. Let's see, notice that there's no bubbles on any of the clock inputs. There's also no clock enable. This guy is just going to run on the clock, and nothing else is going to happen. And we have 7 through 0. So we got 6, 5, 4, 3, 2, 1, and then 0. And if we look at the timing diagram, the take-home message here is that, the exam question is, how many, at the start of an 8-bit serial in, serial out shift register, how many clock cycles will it take for the first bit to reach the output? And the answer is 1 less than the number of bits. So on this very first rising edge at 2 is when serial in, that first flip-flop is going to pick up the value at serial in. And it's going to take, 1, 2, 3, 4, 5, 6, 7 for that one to appear at serial out. So you get the first flip-flop for free, or the last one for free, I guess is really more accurate. And so it'll delay, an 8-bit serial shift register will delay 7 clock cycles. So that means if you have a 16-bit serial in, serial out shift register, then your delay is going to be 15 clock cycles. And then you can see once stuff starts coming out, serial out is going to look exactly the same as serial in. Right? Because no processing is happening, no manipulation happens. It's just the bits are coming in and they're just getting shot out to the end there. So a serial in, serial out shift register is not on its own entirely useful. There's really not a whole lot of applications for why you would just want to sort of delay some data a number of clock cycles, besides timing, I guess. But what's more common is what's going to come next, which is this, the parallel in, parallel out shift register. Here's our block diagram for it. We've got a couple of things. Let's see, we've got here, we call it parallel in, parallel out because it has parallel in and parallel out, but also notice that it has a serial in and a serial out. So we have the sort of best of both worlds, right? We got some serial in data coming, we got some serial out going out. Notice that serial out is just, the last flip-flop value. Serial in is just going to be the first serial input. But now we've got 2 control inputs. We've got shift enable and load enable. And let's take a look and see what is going on with this. And it works by having these multiplexers inside the shift register that's going to select between some different stuff. So notice that the selects, the control inputs to our multiplexers come from SH's, I'm going to write it up here, SH equals shift enable, and L equals load enable. Right? And that's going to drive the multiplexer. The clock is just running. Hey, look, there's a bubble, which means that it's a falling edge. But there's no enable on the clocks, which means the flip-flops are always just going to keep churning, right? They're always going to be trying to update on every cycle of the clock, and we're going to use this mux to kind of lock in what's going to happen. So let's look at all 4 cases here. Let's say case 0, 0 is SH equals 0 and L equals 0. And this will be, nothing happens. Right? And we can see that nothing happens because the input to the multiplexer for 0, 0 is just tied to the output, right? So this is saying, well, we're going to take the output of the flip-flop and we're going to pass it back around. And if we've got 0, 0 on the mux, we want nothing to happen. We don't want anything to update. So just keep feeding it its output again, right? Just constantly be providing that feedback to keep it so the value of the flip-flop never changes. Same, you can see and this is mirrored on all 4 of these flip-flops. So that's case 1. Let's talk about that's case 0. Let's talk about case 1, right, which is 0, 1. So that's SH equals 0 and load equals 1. And here what's going to happen is parallel load. So notice that the 0, I'll use this one, the 0, 1 input is tied to the parallel input. So when SH is 0 and load equals 1, we want to grab this input and pass it as the value to the flip-flop, right? And the same thing for D3 and D1 and D0 all the way down the line, right? So we're going to grab parallel input and dump it in. Now let's take a look at case 1, 0. This is where SH is equal to 1 and L is equal to 1, and this is shift, right? And we can see that by noticing that, or I'll use this one, right? For 1, 0, that input is tied directly to the output of the previous shift register, or in the case of the first one, to the shift enable, right? So this means that when shift is equal to 1, we want to actually do the shifting, right? We want to pass the bits down to the outputs. And also, case 1, 1, which is SH equals 1 and load equals 1, we also want to shift, right? It wouldn't make sense to load and shift at the same time, or at least load and shift simultaneously. So what this design does is it says, well, let's just take the parallel, or excuse me, the serial input and tie it directly, right? So this is tied to both of them. So in the case where shift is 1, we don't care what L is. Shift gets priority. If shift is 1, then L is a don't care, and we're going to shift the bits. Right, and that's serial SER out right there. So that's our parallel in, parallel out shift register, right? We're using the values of SH and L to determine what we're going to do. 0, 0 means don't do anything, don't update. L equals 1 means we're going to, L equals 1 and shift equals 0 means we're going to load parallel data into the shift register. And if shift is 1, it doesn't matter what L is, we're going to just shift data to the right. So, any questions about the parallel out, parallel in shift register? Okay, so let's take a little bit of a deeper dive. Let's take a look at its operation, right? This is our state table for the shift register, and everything here is kind of happening the way we would expect, right? So when shift is 0 and load is 0, nothing happens, right? The next state is equal to the previous state. When shift is 0 and load is 1, then we're loading from parallel input, right? So the next state is equal to the parallel input for that flip-flop. Q0 is equal to D0. Q2 is equal to D2. And then if shift is 1, then look, notice that L is a don't care, and we're going to pull from the previous one. The first one grabs from serial input, but from now on, Q2 grabs from the previous state of Q3. Q1 grabs from Q2. Q0 grabs from Q1. And we pass it down. We can derive our characteristic equations this way. I'll do Q3 plus. And it's pretty simple. Q3 plus is equal to Q3 when shift and load are both 0. So Q3 and SH prime and L prime. Or it's going to be D3 when SH is 0, so and SH prime, but load is 1, so SH prime and L. Or it's going to be SI when shift is 1, so SI and shift. Not a lot of optimization to happen there. So now we can take a look and see those expressions. Q3 is exactly what we just drew. Q3 and SH prime and L prime. D3 and load and SH prime. And then serial in and SH all the way down the list. Any questions about the characteristic equations for these guys? All right, keeping it going. So let's take a look at the timing diagram for this. So let's see, a couple things. We've got our clock that's running. Remember, it's if we go all the way back, it's a falling edge shift register. So now if we look here, all the things are going to happen on the falling edges of the clock. So the first thing that happens is that load goes to 1, shift stays at 0. So that means our flip-flops are going to grab whatever the values are on those inputs. So here it says D3, D1, D0 also goes to 1. So what that means is that D0 is going to stay D2 is going to stay the same. So that's going to be 1, 0, 1, 1. And so on the next falling edge of the clock, since load is 1 and shift is 0, the flip-flops are going to grab from parallel input and update with exactly what you'd expect, 1, 0, 1, 1. Then before the next falling edge, shift goes to 1 and load goes to 0. And I guess it wouldn't matter what load does, but shift goes to 1. And now on every falling edge, here we can see that the shifting is indeed happening, right? So the 1 is progressing through the shift register. The 0 is going through right there. And then here on the very last one, shift goes to 0. So we have the 0, 0 case. And notice that everything is zeroed out except for the last bit there is 1. The last flip-flop is 1. And so that's just going to sort of stay there at 1 forever until the next thing happens. And then Q3, notice that it's 0, 0, 0. Well, that's dependent on the fact that, SN, serial in, is equal to 0. If serial in was equal to 1, then we'd update with 1s by default. But here they're assuming that serial in, SN, is equal to 0. So, any questions about this timing diagram? So an exam question here might be something like, in a parallel in, parallel out shift register, if the values of the flip-flops are 1, 0, 1, 1, and load is equal to 0 and shift is equal to 1, on the next falling edge, what will be the values of the flip-flops? Stuff like that. Joshua says, when we call a shift register 4-bit or 8-bit or something like that, does the number of bits refer to the SI bus or something else? Okay, so that question is a little bit... I think there's some confusion in the question itself. So there is no SI bus. So serial in is always 1 bit, right? Serial data is 1 bit all the time. But we're referring to the number of flip-flops, right? So here is a 4-bit parallel in, parallel out shift register, right? But SI itself, SI never has a bus. There's never going to be a 4-bit serial bus. That doesn't happen. Serial is 1 bit all the time. Did that answer your question, Joshua? Cool. All right. That's a good question. Boom, boom. All right. Let's take a look at shift registers with inverted feedback. So here is a 3-bit, just regular right shift register, but notice that the output, the inverted output of the last shift register is coming back around to the input. This is going to have an interesting effect. Also notice there's no bubbles, which means that these are rising edge flip-flops. So if I have let's say I have a 1 here, all right, then I got a 1 there on the next clock cycle, then I get a 1 here, but then I got a 1 there, which means I'm going to have a 0 on this output, and it's going to come back around as a 0. So here, if I draw this is called a state diagram. It just shows the value of each of the flip-flops. So if I start at 0, 0, 0, the next one will be 1, 0, 0, right? And I've always got a 0 here on the output, which means I'm going to get a 1 on the input. And here I've got a 0 on the output, so I'll have 1, 1 on the next one. But notice that the first one shifted here. Still have a 0 on the last one, which means I get a 1 on the input. And now I've got all 1s because I've shifted all the way down. And now I've got a 1 on the last flip-flop, which means on the next cycle, I'm going to get a 0, right? And that 0 is going to start to walk back around. I've got a 1 on the output, which means I'm going to have a 0 on the next one. And I'm going to come back to 0, 0, and then the cycle will repeat itself, right? And I'll just be constantly sort of going around the circle forever. Except in this weird case where we initialize with 0, 1, 0, means I'll just be toggling back and forth between these two states. So a circuit, a sequential circuit that sort of updates its state and then returns to its initial state and keeps going is called a counter. And we will talk about counters on Friday, but that's basically the gist. This is a really simple counter. Now this count is pretty silly, right? It kind of goes from 0 to 4 to 6 to 7 to 3 to 1 back to 0. This one asks, would that 0, 1, 0 be 1, 1, 0? I'm not sure what you mean. Okay, so here we've got, 0, 1, 0. What about it? Oh, I think I understand, right? You're saying, so shouldn't that have turned into 1, 1, 0? And the answer to that is no, because remember, this one is also going to shift to the right? So this one goes to there, and the 0 flips, causing a 1 there. And then, of course, that 0 shifted right to the middle position. Cool. Yeah, so like I said, this guy is called a counter, although it's sort of a nonsensical counter. But counting, when we say counter, we don't always mean counting in the human sense, right? 0, 1, 2, 3, 4, 5. We just mean progressing through a sequence of states. And that can be anything. So this thing that goes 0, 4, 6, 7, 3, 1, 0, 4, 6, 7. Well, that makes no sense to us in the terms of like human counting. This is still technically called a counting circuit. And so when we think about generalizing that, we're going to have this general shift register counter, which will look like this, right? An in-bit shift register counter will have an in-bit shift register, and it will pass those bits out, so parallel out, to some kind of logic, right? That's going to define what the sequence is. And then those bits will get passed back around one bit at a time to serial in, or based on that logic, one bit will come out to serial in the clock, and then get shifted through and then passed back out again, right? So this is the structure of a generalized version, right? A shift register that's in bits, parallel out to some kind of combinational logic circuit, back around to serial in. So that's our general shift register counter. Any questions about that? All right. So that is the end of our sort of PowerPoint portion of today's lecture. Just to recap, we talked about a right shift register. We looked at an 8-bit serial in, serial out shift register. We sort of expanded on that and had a parallel in, parallel out shift register. Don't forget that parallel in, parallel out also still includes serial in, serial out. We talked about its operation. We looked at its timing diagrams. And then we saw how a shift register with an inverted feedback creates kind of a bizarre little counter. And then we sort of generalize that to have this general model for shift register counter. And then on Friday, of course, we're going to sort of expand on that and build some sophisticated flip-flop counters. So any questions about any of that before we turn it over to Visual Studio Code and look at some Verilog? All right, man, let's do the fun stuff then. Hey, question. Would you prefer the empty PowerPoint slides or the PowerPoint slides that have all my like scribbles on them? Scribbles? We want the scribbles? All right. In that case, we'll keep the scribbles. Why not both? Porque no los dos? All right. We'll keep the scribbles then. There we go. Scribbled up. All right. So let's go back to our good friend Visual Studio Code. And let me open a folder. Let me be in the desktop. You can see who's asked me for help during my office hours. SEQ demo 2, since we already did this. Could you include the relevant homework answers in the PowerPoint as well? I'll work on that, Joshua. I'll look into it. I'm not going to look into it. All right. So let's talk about some sequential logic in Verilog. So I'm going to call this seq demo.v. And what I want to do is I want to go ahead and actually build. Let's build this guy, this 4-bit serial in, serial out, right shift register with the shift option there. So that's what we're going to build. We're going to build this design exactly the way it is. So make note of that. Have that drawn out in front of you. I'll have it over here on this other monitor for myself. And we'll dig into it. So I'm going to say, make a little comment here. So 4-bit right shift register with shift enable. All right. So module, let's call it top. And let's do this. We need what? We need an SI, an SO for serial in, serial out. We need the shift, and we need a clock. Semicolon end module. All right, so what I need now are my data inputs, data outputs, not data inputs, what am I saying? Outputs, control inputs, my shift register, we'll talk about that in a second, and then my logic circuit. Okay, so let's add my stuff. I only have one data input, and thankfully it's only 1 bit, so input SI. We got 2 control inputs, input shift and input clock. We have 1 output, output SO. I'm gonna call it SO, not S0. SO. And all of that is 1 bit, since it's 1 bit, since it's all serial. But here I'm gonna make my shift register. So what I need to do is create a reg. I wanna do it 4 bits, so I'll go 3 to 0. And I'll call it just shift register. Just like that. Now notice that it's its own independent thing. It's sort of internal to our circuit, right? Just in the same way that like we have our outputs and our inputs and our outputs, but then we have these flip-flops hanging out in the middle. That's what we're going to do here. In the last class, someone asked me like why I didn't have those defined up here. And that's because if it's not an input or an output, then we don't need to worry about it. So the first thing I want to do is I want to do a combinational assignment. So I want to make sure and say that the output of the last shift register, the last flip-flop, is tied to S out. So that's what I'll do first. So I'm going to say assign SO equals shift register 0. So the 0th indexed shift register. And then I need to do my sequential logic. So and by sequential logic, I mean now the behavior of my flip-flops. So the first thing to do is we need to make sure that all our flip-flops trigger on the positive edge, the rising edge of the clock. So that's what we want to do first. So to do that, here's where we really need to use that always at business. So I'm going to say always at pos edge of the clock. So this says this execute this sequential logic block always at the positive edge of the clock. If I want to do a falling edge or a negative edge, I would say neg edge of the clock. But here, of course, I want to do pos edge. Okay, now all I want to do is sort of make my shift registers do the thing. So I'm going to say shift register 3. And I'll come back to this operator in a second and what it means. Shift register 3 is equal to, this one takes from serial in directly. Then shift register 2 takes from shift register 3. Then shift register 1 takes from shift register 2. And shift register 0 takes from shift register 1. And there we go. And that is it as far as my logic goes. So let's unpack a couple of things. The first thing is this less than or equal to looking business. This is what's called called a blocking assignment. And what that means is in a normal programming language, you are used to code executing from top to bottom. But remember, Verilog is not a programming language and will instead do all kinds of weird stuff. So what I could do is say this. The single assignment operator is what's called a non-blocking assignment. And what that says is, anything could be in these blocks. You know what? I might be making a mistake here. I'm doing this out of order. I'm doing this the wrong way. Well, let's play with it and see what's going on. Let's mess around. So let's keep this right here, this blocking assignment. And also notice that I'm assigning a value here to shift register 0. I'm saying, hey, grab the value from shift register 1. But up here, I've got assign SO equals shift register 0. Right? So this kind of illustrates that, remember, combinational logic in Verilog isn't sequential, right? It doesn't happen in order. And so what that means is I don't have to do all of this and then under here say S0 equals, shift register 0. Because that's not how it works. In fact, if I try to do that, it'll throw an error. So I'm going to leave that up there in my assignment block. But the blocking assignment, yes, that's probably why your initial adder didn't work, Gailey. But the blocking assignment says, hey, do these in order. Do the first one, then the second one, then the third one, then the fourth one. Make sure all of those happen sort of in the right order. So let's go ahead and do our test bench. So seq demo _tb .v. All right, same basic boilerplate stuff. Time scale 1 nanosecond, 100 picoseconds. Include seq demo.v. Then module seq demo _tb. In module. All right. So data inputs, control inputs, outputs, unit under test. And I'm going to add a few things. I'm going to say clock and logic simulation. So a little bit different than our regular one. So let's see. Data inputs, but a lot of the same stuff here. Serial SI. For our data inputs, we have 2 control inputs, one for shift, one for clock. Reg shift, reg clock, and then a wire SO, and then a unit under test. I think I just had it called top. Yep, top. UT, and then SI, SO, shift, and clock. All right. Now the first thing I need to do is actually I need to start by initializing this with a value. And I could initialize everything with a value, but I don't really want to, so I'm not going to. But just I do need to make sure clock is initialized with a value. And the reason for that is we don't want to have to like constantly say like, all right, toggle the clock, set the clock from 1 to 0 in our logic simulation. What we can do instead is do here and say always, wow, spelling, always begin and end clock equals not clock, and run that at like, you know, toggle that every 5 nanoseconds, which means that the clock period is 10 nanoseconds. All right, so this will run the clock. Oh, it's supposed to be a semicolon, you catch. So this means that no matter what we do in our simulation itself, our initial begin and end, right, our simulation, the clock is just going to be running in the background. And so we can just sort of set stuff and then run it and let it work out. So that's what we're going to do here. So I want to say, let's first set SI SN equal to 0, and let's set shift equal to 0. Do all those lines. Let's wait for 20 nanoseconds, right? You want to make sure that you sort of give plenty of time for the clock to be doing its thing. Now let's go ahead and set SI equal to 1. Let's go ahead and leave shift at 0, and let's delay for 20 nanoseconds. Now let's set shift equal to 1 and delay for 20 nanoseconds. So now what should happen is it should start clocking through. And in fact, no, that's fine. And then I want to set SI equal to 0, but I'll leave it shifting. I'll go ahead and let that happen for 40 nanoseconds. No, I'll do 20. And then I want to set shift equal to 0. And let's wait for 20 more nanoseconds, right? So the idea here is that I'm going to set everything at 0. I'm going to set SI to 1. Turn on shift. It'll do a couple clock cycles. And then instead I'll set SI to 0. And so it'll do another couple of clock cycles. And then I'll say shift is equal to 0. And it will probably stop. So any questions about this test bench that we put together? Oop, and we're pretty much out of time, so let's run it and see what we get. So let's do all the normal good stuff. Verilog option O. seqdemo.vvp seqdemo_tb.v. Hey, look at that. No errors. It's probably because I did it before. Liam asks, so the always is not like a while loop in that the code will not get stuck within the loop. No, it won't. Although I'm glad you mentioned that because that reminds me I didn't do the dump file stuff. .vcd dump var 0 seqdemo_tb. Finish. Run that again. And then vvp seqdemo.vvp. Things happen. gtk wave seqdemo.vcd. All right, let's grab our stuff. So the first thing is, all right, so let's see. So we got the clock. Look, the clock's running. Rising edge every 10 nanoseconds. That's nice. Notice that S out is undefined for at least the 1, 2, 3, first 4. That's because, remember, we set shift in SI equal to 0, which means that 0 had to sort of like propagate through. Oh, you know what I forgot to do? Gang. I completely ignored. Sorry, I know we're almost out of time, but this is important. I completely ignored this, the shift, right? We only want to shift when when shift is equal to 1, right? So notice, well, in GTK wave that it was 0, but that 0 is sort of propagated through. So what I'm going to do now actually is say if shift begin and end and put that in. Now that should only run when shift is equal to 0. So here I can have that for loop. Oh, so actually here, check this out. So this is before the change I just made. So you can see that SI, that 0, after 4 clock cycles ended up at the end. That shouldn't have happened because shift was set equal to 0. So let's go back and run our simulation again. Boom. Hey, by the way, pro tip, you don't have to constantly run GTK wave. You can just run your simulation again and then hit reload, and you get all the new stuff. Okay, so now this is working properly, right? Notice that serial out doesn't update until 4 clock cycles after we went to 1 there. And I need to see the bit on the input here. So I can open this up, grab my UUT directly. Now I can access that shift register and append it. Notice that it's going to do some weird stuff. But if I double click, notice that the values in the individual flip-flops, 3, 2, 1, and 0, that 1 sort of trickles through. And you know, one last thing I want to change is I want to change this to delay a lot longer. Let's delay like 80, not 800, 80. And run that again because I want to see it stop. I'm going to reload that. Now, there we go. So let's see. Well, actually, it stops here at 3. Make it do the thing. Let's do this. Let's do 80 there and 20 there. Sorry, I know we're out of time, but I just think this is so cool. All right, there we go. That's something that makes a little bit more sense. All right, so now we can see the clock running. SI goes to 1, but nothing really happens until shift happens. All right, shift goes from 0 to 1. Now you can see that that 1 dumps into here in 3, then 1 cycle later to 2 to 1 to 0. So we essentially have this little pulse at serial in that after 4 o'clock or after a couple clock cycles, right, it only lasts for 2 clock cycles after shift goes to 1. You can see that pulse sort of walk its way through the shift registers and then be out there on the end. Okay, so that was a bit. I apologize for keeping you guys a few minutes over. Are there any questions, comments, concerns? All right. So your sequential logic Verilog project is actually a fair amount easier, I think, than doing this shift register. So I think that's all right. But as always, if you have any questions, comments, concerns, my office hours are still today from 3 to 5. But since nothing is due, I suspect I will be pretty lonely. So yes, Adrian asks, will this lecture be uploaded later? Yep, it'll be uploaded in about 3 minutes as soon as I turn it off. So thank you so much, guys. I'll see you on Friday. Thank you.